For the last 50 years, computing has been built on a really simple promise. Chips get smaller, they get faster, and they get more efficient. But what if I told you a huge part of that promise has actually been broken for over a decade? That's exactly what Nick Harris, the CEO of Lightmatter, is saying. Sure, we're still making transistors smaller, but they've stopped getting more energy efficient. We've basically hit a heat wall. And this isn't just some nerdy technical problem. It's a massive energy problem that could stall the entire AI revolution.
Okay, so let's put a real number on this crisis. 27 gigawatts. Get this, that's how much power AI is expected to need in Texas alone. Now, to put that into perspective, the entire state of Texas normally uses about 100 gigawatts. So we're talking about a single industry in just one state needing almost a third of the entire power grid. That's insane. So how do you power a revolution that's moving that fast? Well, the answer might be to stop pushing electrons around and start guiding light instead.
And that, right there, is what we are diving into today. Thinking with light, the dawn of photonic computing. We're about to explore an idea that's actually from the 1960s, one that was left behind, but might just be the only thing that can power the future of intelligence.
So here's our game plan. First up, in the end of an era, we're going to look at the physical wall we've smashed into. Then we'll get into a resurrected dream and the one breakthrough that made it all possible again. After that, we'll get into the nuts and bolts of how light thinks before we witness the photonic revolution that is happening as we speak. And to wrap it all up, we'll gaze into our luminous future. All right, let's kick things off with section 1. Before we can talk about where we're going, we've got to get our heads around the huge problem we're facing right now.
We all know Moore's Law, right? That old, reliable rhythm of progress that said performance would double every 18 months or so. Well, the AI boom came along and just completely shattered it. Now, the demand for AI performance is doubling every 3.5 months. That's not just a little faster, that's a whole different ballgame. And our traditional silicon chips, they just can't keep up. The result is that the very laws of physics that built the digital age are starting to crack. And you can see exactly how it all fell apart here. It really started around 2005, when a rule called Dennard scaling just broke. You can think of that as the efficiency bonus of Moore's Law, the part of the deal that said smaller transistors would use less power. And poof, it was gone. Then, around 2020, things got really weird. A thing called quantum tunneling kicked in. The transistors got so tiny that electrons, the things carrying the information, literally started ghosting through the walls, wasting energy and causing all sorts of errors. This mess created what we call the memory wall, a fundamental traffic jam on the chip, and it's all fueled by this massive energy crisis. So if the old way is totally broken, where do we go from here? Well, that brings us right to section 2, a resurrected dream. Because, funnily enough, the solution isn't some futuristic sci-fi invention. It's actually an old idea that's finally having its moment. Believe it or not, the idea of computing with photons, particles of light, has been around since the 1960s. Basically since we invented the laser. So why didn't it take off? Simple. Silicon was just too good. It was cheap, it scaled perfectly thanks to Moore's Law, and the entire world built its digital life on it. For decades, light was this cool science project, but electrons were the ones actually paying the bills.
So what changed? What was the big breakthrough? Well, it was something called silicon photonics. And in simple terms, it just means we finally figured out how to build tiny, light-based components, little lenses, mirrors, light tunnels, using the exact same factories that make our regular computer chips. All of a sudden, this old dream wasn't just possible, it was affordable.
All right, so how on earth does a computer actually think with light? Let's get into it in section 3. The whole magic trick here is doing math without generating all that waste heat. But how does that even work? It really just comes down to basic physics. Imagine electrons trying to move through a copper wire. It's like a mosh pit. They're all bumping into each other, creating friction, and that friction is heat. It's why your computer gets hot. Now, photons? They're completely different. They're like ghosts. They can pass right through each other in their own little tunnels without any drama. No friction, no heat.
And the special little path that photons travel on, that's called a waveguide. It's basically a microscopic light tunnel carved right into the silicon. It's the optical superhighway that replaces those old, clogged-up copper wires.
Okay, now this is where the real magic happens. You don't even need transistors anymore. You just let physics do the heavy lifting. Let's say you shine 2 beams of light together. If they get brighter, boom, that's an addition, like 1 + 1 = 2. If they cancel each other out and go dark, that's a subtraction. The final pattern of light is the answer. And because it's happening at, well, the speed of light, the calculation is basically instantaneous.
So this isn't just some crazy theory cooked up in a lab. And that brings us to section 4, the photonic revolution. Because companies are building this stuff right now. And the performance numbers, they're just wow. First up, speed. We're talking 10 times faster. Yeah, you heard that right, 10 times faster. Companies like Light Matter are showing that on typical AI tasks, their photonic chips can absolutely blow the doors off the best GPUs out there. It's like skipping an entire decade of progress overnight. All right, next up is efficiency. And honestly, this might be the biggest deal of all. 90% less energy. Remember that insane 27 gigawatt power problem we talked about? Well, this is how you solve it. And then there's the raw clock speed. Get ready for this. A company called Neurophos has a chip that runs at 56 gigahertz. Your top-of-the-line GPU in a data center? It's chugging along at maybe 2.6. This isn't just a step up, it's a whole different universe of speed. This chart really says it all, doesn't it? On the left, you've got the king of the hill, the best electronic chip we know how to make. On the right, the new challenger. We've talked about the insane clock speed difference, but look at that matrix size. Just think of it as how big of a problem the chip can chew on at one time. And this new photonic chip can handle a chunk of data 15 times bigger in a single go. It's the difference between reading a single paragraph and reading an entire chapter in the blink of an eye. So, what does all this actually mean for us? What does a world powered by light-speed computing actually look like? Let's dive into our final section, our luminous future. See, this isn't just about making things faster. It's about doing things that were literally impossible before. In finance, we're talking about trades at the actual speed of light, with almost zero delay. In healthcare, a doctor could find cancer on a CT scan live, while the patient is still in the machine. Climate, you could predict a hurricane's path in minutes instead of hours. And just think of the lives that would save. This is the key to truly self-driving cars and to discovering new medicines faster than ever. But maybe the biggest change, the most profound one, is this. It's not just about giant tech companies getting even more powerful. Because these optical processors are so incredibly efficient, they bring supercomputing power to everyone. Suddenly, a small university lab or a startup can have access to the kind of power that used to be locked away in Silicon Valley. So where does this all end? What's the end game here? It's not just about faster chips, it's about a whole new way to build a brain. The pioneers building this stuff, they talk about linking 1 million of these processors together until they act like a single, giant thinking machine. And if that's not wild enough for you, how about this? The CEO of Light Matter has seriously talked about our hunger for computing getting so big, we might one day have to turn an entire planet, like Mars, into one massive computer. So I'll leave you with this final thought. Everything we've ever built, and even our own brains, it all basically runs on electricity, on or off, 0 or 1. For the very first time, we are building a machine that thinks in a fundamentally different way. It thinks in waves of light, in brightness and darkness and interference. So the question is, if a computer starts to think with light, will it start to perceive our world and maybe even itself in a way we can't even begin to imagine?